SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Power Plant System Engineering, Module 2, Vapor Power System, Part 2. So, in this lecture, our attention will be focused towards turbines, and in the turbine category, we will discuss mainly on reaction turbine. Subsequently, we will talk about velocity triangles. So, having drawn these velocity triangles, then we will be able to find out the operating parameters for the reaction turbines. So, these operating parameters are the power developed by the turbine, we call this as a power output, blade speed, what is the optimum blade speed the turbine should operate. Then we need to find out nozzle efficiency, moving blade efficiency and stage efficiency. So, these quantifications are required for reaction turbines. So, towards the end of lecture, we will try to summarize the two types of turbines we have discussed so far. One is the impulse turbines, which we are discussed in previous two lectures, and reaction turbines. So, let us start the reaction turbines. So, normally the word reaction comes from the Newton's third law of motions. For every action there is a equal and opposite reactions. So, taking that advantage of the law, the reaction turbines are developed. So, prior to that we are going to discuss about this reaction principle. Normally the reaction machines are devices that cause the fluid to exit at high speeds, and this high speed exit fluids gives substantial force onto the body, which means that fluid beginning with zero velocity creates a force in the direction of motion, and there is a corresponding equal force that tends to move the device in the opposite directions. So, a typical examples that we are seeing in our day to day life is, one is that aircraft or rocket when is moving, it is based on the reaction principles, which means that the exhaust that comes out from the rocket nozzles that drives the rocket or aircraft at certain altitudes. Other rotary devices, we can find out the lawn sprinkler, which means that you might have seen machines installed for the gardening purpose in the lawn, which typically rotates, and side by side water jet comes out of it. So, it means that when jet of the water gives a force that rotates the sprinkler in the opposite directions. So, these are the some of the examples of reaction turbines, and similar concept we are going to use while developing the relations for reaction turbines. So, prior to that, what we have seen in the impulse turbines is that there is no pressure drop in the moving blade. So, one can imagine to have a blade passage through which there will be a pressure drop, then blade would have reaction force moving in the opposite directions. So, if you use in the impulse turbine, of course, there is no pressure drop in the moving blades, but if you can imagine that if at all we can create some device which will move the blade when the fluid passes through the blade passage. So, that is the concept of reactions. So, however, in reality a pure reaction blade does not exist, because the blade passage is not a reservoir or where steam can have zero velocity, it will have some finite velocity. So, in reality reaction turbines are partially impulse and partially reactions. Here the term reaction is used despite the fact it is a pure reaction turbine, are not built. So, in other words, many books refer them as a equal pressure or unequal pressure turbines as impulse and reaction turbines. Now, coming back to the concept of reaction turbine in which it works. So, let us understand these figures, and we will see how pressure drops and velocity changes across the blades. You might have aware that when we discussed about impulse turbine, there were a set of nozzles that supplies to the fluids and that rotates and to the moving blades. And there is no pressure drop in the moving blades in an impulse turbine. Whatever pressure drop takes place, that takes place in the nozzle only. Now, you imagine a situation that we can think about an array of fixed and moving blades in a organized fashions, which means that this fixed blade passage acts as a nozzle entry for the moving blades. That means, it supplies the fluid to the moving blade in appropriate or directions with a appropriate orientations as the blades are designed, so that we can maximize the fluid intake, and this is the role of the fixed blades. And once the fluid passes through these moving blades, then again it is goes to the next round of fixed blade, because the fluid may not have sufficient expansion, may not have been to a full extent. It may have certain kinetic energy at the exit of the first set of moving blades. So, they again realigned through another set of fixed blades to the next set of moving blades, and this process continues till the fluid velocity comes down to a very marginal level. So, accordingly what happens, if you look at the absolute velocity, so in the fixed blades this the velocity increases, and of course pressure decreases, and in the moving blades the velocity decreases, again in the fixed blade it is increases and it decreases. The side by side there is a continuous increase and decrease in the velocity, but if you look at the pressure drop is very gradual. So, at the however, one point that to be noticed is that at the initial stage the slope is little bit high, but when you run for the towards the later stage, the slope may be less, because the fluid loses the energy in a subsequent stages. So, this is how the reaction turbines work. The reaction turbine is constructed through rows of fixed blades and rows of moving blades, and here the fixed blades act as nozzles. The moving blades move as a result of impulse of the stream received through the change in the momentum, and also as an expansion and acceleration of the stream relative to them. This particular picture shows a 3-stage reaction turbines. That means, there are 3 sets of fixed blades and 3 sets of moving blades. Now, moving further, if you want to quantify the fluid energy in terms of enthalpy, we can say that the enthalpy drop per stage it means a one row of fixed blade and one row of moving blade is often equal. So, we already have emphasized that it is not possible to construct a complete reaction turbines. It has to be partly impulse and partly reactions. In some sense, we say that or a very reasonable argument could be 50% reaction turbine and 50% in impulse turbine. In other words, it means to us that 50% of enthalpy drop takes place during impulse stage and 50% drop takes place in the reaction stage. That is, 50% drop takes in the moving blade and 50% takes in the fixed blade, and in fact these fixed blades act as the nozzle. So, for that reasons we encounter a parameter which is called as a degree of reactions. Since complete reaction turbine is not possible, that is the reason we define a term what is called degree of reactions, and it is defined as the ratio of enthalpy drop in the moving blade to the enthalpy drop in the stage. Stage means fixed and moving blades. So, this is a, in this figure we say it is a stage 1 and this is stage 2 and this is the third stage. When the pressure drops are not equal, then they may be considered as a pressure compounded impulse turbines. So, the concept of pressure drop in a pressure compounded turbine and a reaction turbines are more or less same, but the viewpoint is different, because when you say the pressure drops are not equal, we normally refer them as a pressure compounded impulse turbines, which we discussed earlier. But when they are equal, we say it is a completely 50% reaction and 50% impulse mode. Now, this word 50% is very vital in terms of steam power plant terminology, because this concept of reaction turbine was first invented by C. A. Parson. So, that is the reason this is called as a Parson turbine, which has 50% degree of reactions, and he has developed a 3 stage of 3 reaction stages, each composed of a row of fixed blades and a row of moving blades. Now, the stationary blades are designed in such a way that passage between them form a flow area of the nozzle, and these are the nozzles with full stream admission around the rotor periphery. Now, coming back to the distinguishable features, like if you look at fixed and moving blades or fixed impulse turbines and reaction turbines, normally the reaction turbines have moving blades, and these blades designs are little bit different than that of impulse blade, and they are generally curved in the opposite directions to perform a nozzle actions, and they are aligned with the fixed blade in such a way that fluid is directed in a unified directions, so that complete coverage of this fluid in the moving blades is accounted. Now, one interesting thing or maybe significant inference for this reaction turbine is that the pressure continually drops through all the rows of the blades, whether it is a fixed as well as moving, but the pressure changes is greater at higher pressures. That means, slope is high in the beginning stage and slope is less at the later stage, high slope and it is low slope, which says that pressure change is greater at higher pressures. So, the absolute velocity changes within each stage and that repeats from the stage to stage. So, the fluid passage, it can come like this, goes like this, then again enters the stage next set of fixed blades, second stage of moving blades, then next stage of fixed blades and then next stage of moving blades. So, this is how the orientation of the locus or path of the fluid that takes place when in a reaction turbine. Now, to analyze this performance of reaction turbine, the most important thing that we need to discuss is the velocity triangles, because this mechanics principle based on the drawing the velocity diagrams will help us, which help us in 2 things. One is in designing the blades with their appropriate angle, number 1. Number 2 is that the component of velocity that justifies the power. So, one thing we have blade velocity, other thing is that the fluid velocity that comes out from the exit. So, these 2 things we need to find out while calculating the power developed from the turbines. So, typical velocity diagram for a 2 stage is given in this picture. So, firstly enthalpy drop per stage is defined and it is further divided into 2 parts, one is fixed part and moving parts. That means, if you want to design a set of things, first thing we need to know how much power, our expectation of power we have. Then we have to divide them in 2 parts, one is fixed part, other is moving parts. Now, in the fixed part we have to see how many stages of fixed part is required and how many stages in the moving part of the required. Once you have these numbers, then we can design the blades and align them accordingly. Now, after that the work done of a reaction turbine can be obtained through momentum impulse principles, that is change in the momentum on the blade in a positive directions is nothing but the change of the components of relative velocities in that direction. So, we will see how this velocity diagram look like. As I told, the direction of the fluid that comes here and enters from the fixed blade, then enters to the moving blades, then further enters to the fixed blade, then goes from the moving blades and finally it comes out. So, this fluid passage continuously have this. So, basically seeing, if you take one particular stage, we have one fast blade category, that is fixed blade. For this fixed blade we can see Vs1 is the velocity flow of fluid that enters, Vb is your fluid blade velocity, and this gives a relative velocity of the fluid that enters. So, when you see the moving blades, it enters at Vr1 and it goes at Vs2, this will be Vr2. So, we have Vr1, Vr2, Vs1, Vs2, Vb is the blade velocity. Similarly, next stage we have Vs3, the fluid velocity, relative velocity of the fluid Vr3, and blade velocity is Vb. So, likewise the velocity diagrams can be constructed, and here the theta normally refers to the angle at which the absolute velocity of the fluid enters into the moving blades, and phi was the relative velocity of the fluid when it enters to the moving blades. So, these angles are very vital because this gives the orientation of the blade. Now, coming back to the mathematical insight, we need to find out at the end of our analysis is that what are the working equations and how much power we are going to get it. So, for that reasons the velocity diagram with respect to enthalpy drop in the fixed and moving parts of the turbine has to be analyzed. So, if you say enthalpy drop per stage, that means if you are considering n number of stages, so the total enthalpy drop, that means drop per stage is delta H is equal to delta Hs by n, n is stands for number of stages, and for each now we are saying that it is a Parsons turbine. So, 50% has to drop has to take place in the moving fixed blade and 50% has to take in the moving blades. So, you can divide them equally. Then from this velocity triangle one can find out what is the delta Hf and delta Hm, and again from this velocity triangle we can also find out by combining to one set for one stage, we can find out the combined equations of this relative velocity, stream velocity and blade velocity. Then ultimately we can find out change in the momentum on the blade in the direction of positive x directions. So, we can find out F. So, from the F we can find out the rate of power, and subsequently the final expression that we are going to use, this is a general expressions of turbo machinery principle, which says that W dot would be m dot by 2 into whole divided by Vs1 square minus Vs2 square minus Vr1 square minus Vr2 square. So, this is the final expression that we are going to use. Then after having calculating the work output from the turbine, we will be able to find out the optimum blade speed at which the reaction turbine should operate. For that reasons we need to find out, since we have already assumed to be a 50% reactions. So, based on that there are some assumptions that blades needs to be geometrically similar, for which theta should be equal to gamma, and then that is our user friendly requirement. Then from this we can find out the final expressions for rate of work or power. By assuming these conditions or these blade conditions, then we can find out the expressions for work done or developed by the turbines, and for maximum work we can differentiate this work expressions with respect to Vb, and we will get the optimum blade velocity. And you see your optimum blade velocity is Vs1 cos theta, whereas in other cases it was Vs1 cos theta by 2. That means in a reaction turbine we are able to operate it at a higher blade speed. Then from this we can also find out the maximum work. So, this is how the blade design of reaction turbines is all about. And now after having said this, we will be now looking into the efficiency part. So, here efficiency, when you talk efficiency, here we see that enthalpy drop takes place both in fixed blade and moving blades. So, for that we have fixed blade efficiency, we have also moving blade efficiency, and of course, the fixed blade and moving blade they constitute a stage. So, that means we have a stage efficiency. So, once we have everything, then again we can think of the enthalpy drop that takes place in an isentropic manner or in an actual manner. So, considering all these things, we have to revisit this Mollier diagram, which is normally done with enthalpy and entropy, and this is normally done for all types of reaction turbines, and we call it as a condition curve. That means, what is the condition of fluid when it expands in each stage. So, what has been plotted here in this Mollier diagrams, we have the saturation line. On this saturation lines, these are the constant pressure lines, that is P naught, constant pressure lines P naught, P1, P2, P3 and P4. So, interesting fact is that when you go along this pressure line, the divergence, that means the divergence is higher, that means higher you go, the divergence becomes higher and higher. So, we take this advantage, that means if you draw a vertical line at this location and if you draw a vertical line at this location for same pressure difference, this the second case enthalpy drop will be higher. So, we take this advantage as what happens in a fixed blade and moving blades. So, that is one thing. Second thing, that means when you go for higher pressure, that is the advantage, that when you go for higher pressures, we have a larger enthalpy drop which is available to us. So, this gives a higher power output, that means higher pressure drop or superheated steam at higher pressure and temperature gives a higher enthalpy drop. So, we take this as an advantage and we keep heating the fluid. That is one thing. Second thing, that when you look at the drop actually, that means if a fluid which is initially at state 0 and it expands to a 4, this is the final realistic curve, that means this is the actual final enthalpy drop that takes place from 0 to 4. But in between what happens? It passes through a fixed blade, moving blade, fixed blade, moving blade. So, correspondingly the points are located as 1, 2, 3 and 4. Now, what we are saying that, for example, if at state 1 had this process been isentropic, then it would have landed as 1 to S. From point 2 had this process been an isentropic, then drop would have been 2 to 3S, isentropic drop would have been this. So, likewise these dotted lines signifies all these numbers. And finally, in fact, if you totally ignore all types of blades, if the fluid drops from 0 to 4, it would have been 0 to 4 Ts, isentropic drop would be 0 to 4 Ts, but actual drop is 0 to 4. So, this logic we are going to use to define the terms which are called as fixed blade efficiency, moving blade efficiency and stage efficiency. And for that where the actual expansion curve, that is 0, 1, 2, 3, 4 is referred as condition curve. Of course, from the Mollier diagrams we take the advantage that the constant pressure lines diverge to the right side of the Mollier diagrams. So, that means the enthalpy drop change to row or stage is greater than the succession rows or stage for an entire turbine. Now, looking at our explanation like this, first thing we define the term what is called as a degree of reactions, which is defined as the ratio enthalpy drop in the moving blade divided by enthalpy of drop from the stage. And referring to the figure, we say it is H1 minus H2. If you say one set of fixed blade and moving blade, we say it is H1 minus H2 divided by H0 minus H2. Now, if you stay first stage, second stage, third stage, whatever I explained, that delta HF means fixed blade isentropic enthalpy in the fixed blade, and delta HMS means isentropic enthalpy for moving blades. So, we can find out for first stage what is happening and second stage what is happening, and effectively they are normally equal because we have assumed in that way. Then we can see that one particular term, that is H0 minus H2S plus H2 minus H4S is actually greater than H0 minus H4SS, which means the constant pressure lines diverge when you go for higher entropy and enthalpy. Then we are now in able to positions to define what is fixed blade efficiency, and we normally refer as the nozzle efficiency. It is nothing but the ratio of kinetic energy change to the isentropic energy change across the flexed blade. Then for moving blades we have two things. One is already we are saying that 50% enthalpy drop should happen in the moving blade. At the same time there is a kinetic energy which is available from the exit of the first set of blade, from the first set of fixed blades. So, which means that energy which is available is the sum of kinetic energy of incoming stream and isentropic enthalpy drop across it. The stage efficiency of the reaction stage is nothing but the work of the moving blade in the stage divided by isentropic enthalpy drop for the entire stage. So, whatever we have explained, if you represent them as mathematically, then we say nozzle efficiency eta n, which is H0 minus H1 divided by H0 minus H1s. Then moving blade efficiency, which is power developed in the moving blade divided by m dot into Bs1 square by 2 plus H1 minus H2s. Then we have stage efficiency, that is W dot by divided by m dot into H dot minus H2ss. And for the terms that we are going to use, we have to use this condition curve. So, we are now able to understand how the reaction turbines work, what is its working principles. Now, before you complete, let me summarize what is a reaction turbine and what is an impulse turbine, what we have learned so far. This particular picture summarizes the type of turbines that we have come across in all our lectures so far. So, first thing that we studied is the impulse turbine in a single stage. So, when you say it is a single stage, we have a one row of blades that moves and the fluid receives, and that means the blade receives the fluid from this nozzle and that rotates the blade. So, accordingly we say that complete pressure drop takes place in the nozzle itself and in the moving blades just rotates. So, accordingly we have pressure and velocity diagrams. So, this is what we call as a single stage impulse turbine and which is denoted as D levels turbine. Some modification was done in terms of compounding, where we say that single stage is also difficult because when we are available of steam is at that very high enthalpy, at very superheated steam at very high enthalpy and speed is available, then loss will be more if you go for a single stage. So, the idea was thought of let us do some kind of other approach. So, that compounding approach was done. There are two types of compounding, one was velocity compounding, other was pressure compounding. So, through the velocity compounding, normally this is referred as a Curtis stage. What it says is that let us think about a situation that you instead of losing this entire fluid energy at a single stage or releasing, you keep on doing it with a fixed set of stationary blades. And that means you allowed that exit fluid to pass through another set of stationary blade, then again expand. So, through this process also this entire that pressure line again continued and slowly we drop the velocity gradually in two stages and we call this as a Curtis stage and it is a Curtis turbines. But then there are other advantages that if you have too many high pressure and these things, if the fluid is very also the blade velocity is also needs to be high, then what you do is that instead of when the fluid is of course is available at very high pressure and superheated conditions, another approach people follow is that instead of doing this velocity compounding, do pressure compoundings. That means you remove these stationary blades and same fluid energy you supply to different stage of moving blades. So, here the basic difference between this velocity and pressure compounding is that same set of nozzle is used for all moving blades, but here different nozzles are used or a set of nozzle is used for a set of moving blades. That means there are two nozzles here, whereas it is a single nozzles. Now, through this process we also find this, we also see the advantage that pressure drop which happens, it also falls in stages. So, we have pressure drop in the stages, of course velocity increases during when there is a pressure drop in the nozzle. So, this we call as a pressure compounded impulse turbines. So, it is called as RAT2 turbines, but unfortunately there may not be equal pressure drop in each stages. So, it is not means each pressure compounding turbines. So, what we see here is that a continuous drop in pressure as well as the changes in the velocity. Now, further design which people think in the reaction mode is that instead of doing this unequal pressure stages, you think about a continuous or a smooth curve of pressure drop across all the blades of the turbines. So, what it assumes and this design is called as a Parson turbines, which says that there are let us assume that 50% drop will take place in the fixed blade stage and rest 50% has to be taken into moving blades. And you can see that there is the drop in the that means the pressure drop is very gradual and which is much better than any of these cases. And through this process we have also advantage that we can run the blades at higher velocities. So, these are the some advantages we have, but however, for logistic point of view there are some restrictions that we cannot go, maybe there are more than 2 stage Curtis turbines is not, although it is possible in design, but it is not economical, and when we have very high speed jet which is available to us, it is better to use this pressure compounding rather than reactions. So, there are some relative advantage between reaction and impulse turbines. So, some of them are listed here, that in any turbine the blade speed is limited by the centrifugal stress induced by the blade materials. The stream velocity of reaction turbine is almost half of the pressure compounded turbines, and the reaction turbine is not efficient machines which is suitable for large capacity as compared to impulse turbine. That means, impulse turbines are used for large capacity. On the contrary, the work production in the reaction turbines is almost half of that of an impulse turbine for same blade velocity. So, it says that first point says that reaction turbines are efficient machines for large capacities, but the rate of production of is almost half. The reaction stage has a pressure drop across the moving blade that makes less suitable for work at high pressure, and because it also it adds to steam leakage around the blade tip, which is more steam leakage maybe when there is a when the fixed blades and moving blades are aligned together, there is a possibility of leakage, and this leakage becomes severe at higher pressures. The impulse staging is preferred in the entrance stages of the turbines when the pressures are high and the steam specific volumes are low and the blade height is small. So, this allows low stream velocities. In low pressure stages, the reaction mode is accepted because the pressure change across the moving blade is less. The blades become progressively longer, so that tip clearance becomes smaller relative to the blade height. This is something with respect to the blade designs how we need to be accounted for. Large reaction blading negates the disadvantage of lower pressure drop per stages as compared to impulse turbines for same blade speeds. So, this is all about the overall picture of impulse and reaction turbines. Now, we are able to know all the transient details of impulse and reaction turbines. So, before I conclude this lecture, let me jump into one simple problems which is based on the Parson's turbines. So, normally when the word Parson is used, it is a reaction turbines, and Parson turbines assumes the fact it is a 50% reaction and 50% impulse. So, this is the first assumption you do. Second thing, in terms of velocity triangle, there are certain assumptions that some blade angles are equal. So, which we will come to know when you draw the velocity diagrams. So, the problem statement goes like this: in a Parson turbines, the speed of rotation of blade group means it is a set of moving blades and set of fixed blades and moving blades. These is called as blade groups. They are having an RPM of 3000 RPM. So, 3000 RPM means it has to be converted to the blade velocity as well, and the main blade speed is 100 meter per second. The ratio of blade velocity to the fluid velocity at the moving blade is 0.56. which means that when the fluid comes from the fixed blade and enters to the moving blades, the ratio and when it goes it. So, the ratio which is given, that blade velocity to fluid velocity and the moving blade, that will, this is nothing but it is 0.56. So, exit angle is for the fluid is 20 degree and the mean height of the blade is 25 mm. So, these are the numbers which are used to find out the volume flow rate. So, first question is that we have to draw the velocity diagrams. Second thing, this is asked for the what is the mass flow rate, that means from the mass flow rates we will come to know when you are able to find out the volume flow rate. For the volume flow rate, these dimensions are required. And last statement is that if there are 5 pair of blades in a group, calculate the total enthalpy drop. So, for these problems, so let us recall our again same velocity diagrams which we draw for impulse turbines. Same nomenclature or things that we are going to use. We say that blade velocity Vb. So, this Vs1 in the impulse case it was coming from nozzle, but here it will come from fixed blade, because these fixed blades in this reaction turbines acts as a nozzle. So, here you have Vs1 and this is Vr1 and Vb. So, this is the inlet triangle that is for fixed blade. Then we will at the outlet what we see is something like this. So, it is Vr2, then Vs2, and the angle that we normally are interested, it is gamma, and this is your theta, this angle would be phi. So, this angle is gamma. So, you drop a vertical, here also inlet triangle you drop a vertical. Name these triangles as A, B, C, D, then we have P, R. So, looking at these velocity diagrams, and in fact, in our last problem solutions we will use the same expressions as we are using. For inlet triangle, we can write the expressions as AD is equal to Vr1 sin phi, that is equal to Vs1 sin theta, and we have CD that is equal to Vr1 cos phi, that is equal to Vs1 cos theta minus Vb. So, taking the ratio we can get tan phi, that is equal to Vs1 sin theta divided by Vs1 cos theta minus Vb. Vr1 also another expression we can find out, Vr1 is Vs1 sin phi sin theta divided by sin phi. So, these expressions are required to find out these values, but before you do that, for these Parsons turbines, let us see what are the requirements. So, this for this Parsons turbine, which means 50% reaction, which says that delta H moving blade and delta H fixed blade is delta H total enthalpy drop per stage by 2. This is the first requirement. Again we say theta is equal to gamma, that is 20 degree, just saying that geometrically similar blade. Now, since we have 50% reactions, other assumptions should be Vr2 should be equal to Vs1 and Vr1 is equal to Vs2. These norms are, this has to be considered. And of course, the data which is given velocity of the fluid, this ratio, normally this is called as velocity ratio. So, that is this not be moving blade, we can say velocity ratio would be Vb divided by Vs1. That means Vb and Vs1 ratio, that data is given 0.56. So, these data are given. Other is given is that blade height is Hb 0.25 mm, that is 0.025 meter. N RPM is 3000 RPM, and Vb blade velocity is 100 meter per second. So, from this data, what thing we can find out? We have Vb, that is equal to pi dn by 60. dm means diameter. So, from this we can say dm would be 60 times Vb divided by pi into n, that is 60 into 100 divided by pi into 3000. So, this will give you dm would be twice by pi. So, once you have dm, then we can write down the expression for this volume flow rate. So, this volume flow rate V is nothing but mass into specific volume, and that is also equal to, what is this volume flow rate? Pi dm into Hb, that is volume of the fluid that passes, into Vs1 sin theta. This is what the volume flow rate, that means component of the fluid velocity that takes part into this volume. So, from these expressions we can find out the data for mass flow rate. So, m dot would be pi dm into Hb Vs1 sin theta by V specific volume. So, here that is data, specific volume is 0.65 meter cube per kg. So, what we do not know is Vs1. So, for Vs1 we can find out, we know this velocity ratio, that is Vs1 by Vb by Vs1, Vb by Vs1 0.56. So, Vb is 100. So, this means Vs1 would be 178.6. So, we have Vs1, we know all these numbers, dm, Hb specific volume, Vs1, theta is 20 degree. So, this will give you mass flow rate as pi into dm is twice by pi, Hb is 0.025, Vs1 is 178.6 sin 20 divided by 0.65. So, this will give you mass flow rate is 4.7 kg per second. Now, once you have mass flow rate, then we are going for to calculate the enthalpy drop. Now, since it is a 50% reaction turbine, which means if you recall our work done expressions, that is m dot by 2 general turbo machine principle, Vs1 square minus Vs2 square minus Vr1 square minus Vr2 square. So, this is the total drop. So, W by m dot is nothing but your enthalpy drop per stage, that is delta H stage, but here it is 50% reaction and 50% impulse. So, these expressions we can use it in a different way, and we can rewrite as delta Hm moving blade, because that is our attention, will be half of this. So, half of Bs1 square minus Bs2 square minus Br1 half means it should be 154, R1 square minus Br2 square. By putting this expression for Bs1 Br1 already we have. So, this becomes delta Hm is equal to half Br1 square minus Br2 square minus Br1 square. Okay. So, we have the expressions from the velocity triangles which say from which we can find out. Here Br2 is nothing but Bs1 178.6 meter per second. Br2 we can obtain from this velocity triangles. That means from this data we can find out tan phi is equal to 178.6 sin 20 divided by 178.6 cos 20 minus 100. So, this number is 0.9 and phi is equal to 42 degree. Once phi is 42 degree, then we have Br1 is equal to 178.6 sin 20 divided by sin 42. So, we will have Br1 as 91.3 meter per seconds. So, we have Br2 and Br1. So, this will give you delta Hm, enthalpy drop in the moving blade would be 11.8 kilojoule per kg. So, once we have delta Hm is 11.8 kilojoule per kg, which means delta H fixed blade would be same amount 11.8 kilojoule per kg. So, this plus this will be half, will be total work. So, here we are now able to find out this. So, total enthalpy drop delta H is delta Hf plus delta fixed blade drop and delta H moving blade drop, fixed blade plus moving blade. So, this number is delta H T as 23.6 kilojoule per kg. Okay. So, we are now able to find out the total enthalpy drop per one stage. Now, there are 5 pair of groups and we have m dot, already mass flow rate we have calculated 4.7 kg per second and we have 5 pair. So, total work done W dot would be m dot delta H T into 5. So, which means W dot would be 554.6 kilojoule. So, the part already we have drawn the velocity diagrams. Part B answer is mass flow rate and part C answer is this. So, this gives a broad picture that how a Parsons turbines develops power output while considering both fixed blade and moving blades in an equal manner. So, this concludes this today's lecture. Thank you for your attention.